Hi everybody, and welcome back to our mini-series dedicated to rendering 3D scenes in shaders using the Raymarching method. As you can see in the background of this video, we will bring the previously static scene into life, adding object combinations, rotations along different axes and pivots, multiple lighting sources, and morphing using the so-called smooth minimum. So let's get started. If you haven't gone through the first two episodes, I highly recommend watching them first, as we'll be building on what we covered last time. As for those who would like to get the source code that we'll be expanding, you can download it from my Patreon. The link can be found in the description of this video. So before we begin, I'd like to mention that I have changed the default values of some parameters in the code, mainly the camera and light positions, so that we can continue exactly from the state you see on the screen without any adjustments. Here we can see how the uniform parameters look now in the code and also in the inspector. Camera, light source, and the shadow dist is set to 0.03. Okay, so where do we start? It would probably be best to improve the scene's lighting first. With a single light source, we can render some nice shadows, but parts of the objects remain too indistinct to clearly see all the changes we are about to make. So I'll add a second light, and to make it more flexible, I'll define the color and intensity for each light right away. Okay, so let's find the light source and I will change it to light source 1. Let's keep the coordinates right now. Okay, and since I'm removing that, Godot will complain for a while that the code cannot be compiled, so I'll fix it as quickly as possible. All right, this is the first one, and uniform vec3 light color 1, and with a hint source color, and let's put it to vec3, and the first light, for example, something bluish or maybe violet. We'll see. Okay, this is the light color and the light energy to define the intensity of the lighting, and this can be float. So uniform float light energy 1. It will have a hint range and the initial value, let's have it at 1 maximum energy, from 0 to 1 and 0.01 as the step. Okay, this is the first one, and I will just copy paste to create the second light source. Change suffixes to 2, 2, 2, 2, and this one I think we can put it to negative 1.5 and 5 and negative 2 to give it to the other side, so that the scene is illuminated from both sides and it looks definitely better and in more details. Light color, we can make it reddish, just red, and no, sorry, this is energy. Color is here, and 1, 0, 0. Okay, and finally the light energy, I think we can start at half the energy, 0.5. All right, let's open it in the well, we cannot yet because it cannot be compiled. So let's scroll down to the getLight function. I will just expand the pane a little bit. And now we need more parameters here. First, light source. So vec3 light source. Now vec3 color, vec3 and float energy. Okay. And of course, as we can see, I also changed the return value to vector 3. So we need to change it here. It would be diffuse multiplied by color to get the vector 3 to return. Okay, and now since the method signature has changed, we also need to update its call in the fragment function. This one. So not float diffuse, but vec3 diffuse, and get light with the parameters p, then light source 1, here it is, light color 1, and light energy 1. This is the first one, and we can already see that it is somewhat bluish here. Let's add the second light source, so we will simply add it to the first one. Diffuse is increased by, so it will just increase the intensity, but now we'll change it to light source 2, light color 2, and light energy 2. Perfect, and we no longer need to call vec3 on diffuse because diffuse is already a vector 3, so let's change it to just color is diffuse. Very well, but it seems like we forgot to apply the energy. So let's get back to the getLight function. Here it is, and I think we can multiply it here. Energy. Okay, wait for it. Perfect. Now all is set. We have a mix of red and light blue light coming from different angles. If that unusual color combination is distracting, you can simply change both colors to white in the inspector. And you know what? I think I'll do that. I just wanted to demonstrate that we can use colored lighting, but a black and white scene will probably be clearer and will also make the double shadows stand out better. So I will find the colors here and change both to white, the first one, and the second one. Okay, maybe it's too overexposed, so let's decrease the intensity of both light sources. Okay, and we can see the first shadow and the second shadow and their intersection, and the scene is definitely better illuminated. Okay, let's do it this way. Perfect. And let's move on. As I promised, we'll be combining objects using a method called Constructive Solid Geometry, or CSG for short, which you can also use in the Godot editor for prototyping 3D scenes. Essentially, we need to define three basic operations: intersection, union, and difference. All of these functions are very simple, so let's write them right away. I will scroll up and put them just above the SDF functions. Let's start here. Float, intersect, and float A, float B. These are basically the distances we want to compare. So in this case, we are returning the maximum value of A and B. A, B, and that's it, nothing else. Similarly, we will create the union and the difference. I think I can copy paste twice, 1, 2, and rename the first one to union. And I think it will be better to give it the SDF suffix. SDF, and this time it is minimum. And the last one, difference. SDF, and it is maximum of A and negative B, because in case of a difference, we are interested in the space outside the object. As we know, SDF is positive outside the object, 0 on the surface, and negative inside. Or is it vice versa? I'm not sure. Anyway, this is important. The minus sign indicates that we are doing the inverse operation of this function and comparing one object with its complement, and this is exactly the difference. Okay, and we'll test them right away. First, I'll add a new cube to the SDF function and place it at the same coordinates as our sphere. Let me scroll down. Here is the SDF function. So after the cuboid, I will add cube. And as I said, it will be at the sphere coordinates. So it should be 0, 1.5, and 5. Let's just copy and paste these parameters. Okay. And let's make it a perfect cube. So all dimensions should be the same. 1.5, 1.5, and 1.5 here. Very well. So we have a new object. Let's display it and let's try the union first. I think we can put it here. Here's the sphere. So instead of sphere, we will use union SDF of sphere and cube. Wait for it. Okay. Looks nice. Well, currently our code doesn't include rotations, so we are looking at the object from the front and we can move the camera a bit, I guess. Let's try something like, yeah, we can do this and we can put it up or down. So there is some way to look at that, but it might be better if we can rotate more. So we'll definitely get rotations later. Or, you know what, let's add them right now. It's a simple piece of code and the result will be quite useful. So, how does it work? Rotations around the X, Y, and Z axis can be easily implemented using a 3x3 rotation matrix. We'll write functions for these three types of rotation. So in the code, I'll scroll up again, and in front of this intersect union and difference SDF functions, I'll put the rotation functions. Okay, so we are returning the 3x3 matrix, mat3, and let's start with the X. Rotate X, float theta, which is the angle of rotation. And now, similarly to the two-dimensional rotation, we need cosine and sine of this angle. So let's add it to these variables. Float C is cosine theta, and float S would be sine of theta. Very well, and now the matrix. I think I'll expand that a little bit so we can see the whole matrix. Return mat3, which is defined by the combination of three vectors. Vec3, 1, 0, 0. The second row is vec3, 0, C, negative S, and the third one, vector 3, 0, S, C. Okay, this is the first rotation around the x-axis. Let's copy and paste and create rotations around the other ones. 1, 2. I think I'll just expand everything so we can see all of them. So this is the X, this would be the Y, and this is Z. And what we need to change are the coefficients in the matrix. So for Y, it is actually C, 0, and S. Here it would be 0, 1, and 0, 0. And the last line is negative S, 0, and C. Okay, and the Z-axis rotation, we need C, negative S, 0, S, C, 0, and 0, 0, 1. If you're interested in how I found these coefficients, you can simply Google it up. Wikipedia is full of these formulas or other sources of this information. Anyway, we have it already. And now we can apply that. So if we want an object to rotate around its axis, in this case a cuboid, so let's find the function cuboid SDF. Here's the one. We will simply add a line like this to its SDF function. So we have point P and rotate him. P is rotate Y, and the parameter will be simply time. So it is a continuous rotation, and this matrix will multiply the original vector. Wait for it. Here we go. Now it's rotating nicely, and we can clearly see that the union actually looks like we've pushed the sphere and the cube into each other. If the scene is too... no, the scene is fine. Perfect. And this is the union. How about the intersection? Let's scroll down to the SDF function, and instead of union SDF, we'll use intersection SDF. I'll just copy and paste to make it faster. Here it is, and scroll down and replace. Wait for it. Okay. The intersection truly displays only what is common to both objects. Now, we just need to test the difference. Where is the difference? Here, copy and replace. And look at that. With the difference, we can clearly see that this operation is not commutative, meaning the order of the arguments, sphere and cube, matters. Currently, we are subtracting the cube from the sphere, but it will look better if we subtract the sphere from the cube. So let's change the order. Cut and copy and wait. There we go. Very well. We have something like a hollow cube, and we'll stick with this combination. We'll improve it a bit more and try to cut off the corners of the cube. We'll achieve this by performing an intersection with a slightly larger sphere. Let's add it first. So we have a sphere now. I'll just copy that and paste here and call it sphere 2. And as I said, it should be a bit larger. So instead of 1, let's make it 1.2. Okay, and we'll combine it using the intersection. So I would again copy the name. Where is it here? Intersect SDF. And we have the difference, and let's wrap it. Let's wrap the intersection around that. Okay, and the second parameter is sphere 2. Okay, wait for it, and the corners are cut. If you are unsure about the dimensions for the intersection, let's do the union first, so both objects are visible, like this. Union SDF. And we can see that the new sphere is indeed smaller than the cube, so the intersection will truly remove the protruding corners. If we just get back to the intersection, yeah, here it is. Okay, and what about the cylinder? Let's give it a slower rotation around the x-axis for a change. I will find the cylinder SDF, here it is, and B is rotate x of time, and I said we'll make it slower, so let's multiply the time by 0.5 to make it twice as slower, and multiply by b. Very well, that's not bad. However, we are still rotating around the object's own axis. What if we wanted to use a different pivot? That's easy. We'll simply subtract such a point from the rotation result. So here we have it, the rotation result, and let's subtract, for instance, vector 3, 0, 1, 2. Okay, that's really nice. Maybe we could move the camera a bit farther away so we can see all of it. Where is the camera? Here, and we want to change the Z coordinate. Yeah, that should be fine. Okay. So, what's left? It would definitely be nice if objects that are close to each other could merge into a smooth structure, as you could have observed at the start of this video, much like metaballs that we created in another video. But how we can achieve that in 3D? There is a great website that defines the concept of smooth minimum and will use exactly this method to perform the blending. As we can see, there are several ways to calculate this smooth minimum, or SMIN for short. I've chosen circular, and to avoid any typos, I will just copy it directly. Okay, so I've expanded the shader editor, and right after the rotate Z function, I will paste this one as min, and it is exactly as you could have seen at the site I've been referring to. All right, now we just need to replace the regular minimum. Let's just show the scene. A regular minimum with the smooth minimum in the union SDF function. Let's use for k, this one. Let's use some small number like point 0.1. All right, so union here. So instead of min, it would be smin, and the third parameter 0.1. Okay, no change. Yeah, right. We are combining with the ground, and we are still using the regular minimum for that. If you scroll down to the SDF function, there is min. Can you see it? So we need to replace that right now. I will do it. Union, union SDF. Okay, and wait for the cylinder to hit the ground. Yeah, something is there. I think we can just fix the camera position to better see it and move it to X. And yes, we should see the morphing part, the blending, I would say. Okay, maybe if I just show the other part when it's emerging from the ground. Yeah, this is much better. Okay, and to make the scene complete, let's add a third sphere and perform its blending with this cuboid. So we have sphere 2. I will just copy and paste to create the sphere 3 and give it these parameters. So it would be vector 3, negative 3.5, then 1.5, this is correct, and 5, this is correct too. And the diameter, I think it can be 1. All right, and now we want to combine it with the cuboid, which is here. So instead of just cuboid, I will use union SDF applied on cuboid and the new sphere. So union, okay, it seems to be too long. So I will, sphere 3, I will move it a little bit. Now I'm not sure how many brackets. Too much? No, one more. Okay, this is okay. And we can see here in this part, like the cuboid is blending with the sphere, which is too close to it. So it's actually intersecting. If I move the camera again, yeah, now it should be better to observe. Great. And we are done. I think we can admire the result. I'll just reset the camera position. And mostly we can see all of it. If not, I will again zoom it out, and now we can see all of it. All right. Thank you very much for watching, and I hope you enjoyed exploring the additional possibilities that Raymarching offers. I'll also upload this final code to my Patreon account, so it will be available to anyone who decides to support the creation of more videos and tutorials. This series will definitely continue, as there are many other interesting topics, such as setting up materials for advanced lighting, refraction and reflection, or using Raymarching to create 3D fractals, and much more. For now, take care, good luck with your projects, and I'll see you in the next video.